All right, let's deep dive into how SpeedKit works on your stack. Let's start with the question why websites are not loading instantly today and take a look at the bottlenecks. Suppose a user landed on your site and now wants to navigate to the next page by clicking a product. Now the browser sends a navigation request to your server to get the HTML document. This is the first bottleneck, as it causes backend processing to generate the page, often from various database queries or information from subsystems. When the HTML is received by the browser, it parses the document to discover needed resources, which are also loaded over the network. The loading of those resources over the network is the second bottleneck, also called the critical rendering path. The last bottleneck is that the browser needs to combine these resources to render the page by building the DOM, CSS object model, and render tree before painting the pixels on the screen. All of these bottlenecks prevent the navigation from rendering instantly. While there are optimization techniques for every one of these bottlenecks, traditional approaches can never get rid of them entirely. This is why SpeedKit goes a different route by changing how the website is loaded. Instead of reacting to navigations, we will anticipate them. Let's take a look at how that works in detail. With SpeedKit, we're starting in the same scenario. The user has landed on the site and is looking for the next page to navigate to. SpeedKit is installed right in the user browser by registering a service worker that orchestrates the navigation process. While the user is looking at the page, SpeedKit predicts the most likely next page the user will navigate to. We use machine learning based on real user monitoring data and user behavior on the device to ensure high accuracy. We will deep dive into the details on a later slide. The predicted pages will be pre-cached into the user's browser. This pre-caching happens completely on SpeedKit's infrastructure and does not increase the load on your origin servers. To enable that, SpeedKit caches an anonymous version of the page on its globally distributed caching infrastructure while ensuring personalization is applied dynamically. More on this dynamic caching on the next slide. The big advantage of this is that we process the page already in the background before the user started the navigation. On Chromium-based browsers, Chrome, Edge, Samsung, and some more, we go one step further and fully pre-render the page in a background tab. This means when the user clicks a link, the page is ready and simply gets switched into the foreground, resulting in an instant navigation. Since the pre-rendered page is an anonymously cached version, personalized content needs to be loaded. For that, the service worker issues the original HTML request to your origin server as soon as the user starts the navigation. The request gets the personalized HTML back, which is automatically merged into the rendered DOM and starts the normal JavaScript execution. This way, we ensure instant navigations while at the same time showing the fully personalized and up-to-date page to the user. What makes this approach so successful is that our prediction system successfully identifies over 85% of navigations, we do not increase the load or cost on your infrastructure, we ensure pre-rendering is fully side effect free. For example, analytics is only executed once the user actually navigates. And finally, we manage client resources carefully and monitor the effects closely via real user monitoring. We use, for example, dictionary compression to save 90% of bandwidth, and we only execute JS when the user actually navigates. This was a very quick overview of how SpeedKit delivers instant navigations. For a deeper understanding, I would like to discuss the approaches in a bit more detail. I would propose we first take a deeper look into dynamic caching before diving into the prediction mechanism. Zooming into how the dynamic caching works, we use the same situation as before, but remove the prediction part for now. We're starting on the loaded page again, just before the user clicks a link. When the user navigates, the service worker intercepts the navigation request, and instead of sending one HTML request, it sends two requests in parallel. One request is an anonymous one, which means it has no cookie attached to it. This goes to the SpeedKit infrastructure to retrieve the anonymously cached page. You can think of the response that comes back as the version that the Google bot would receive. The second parallel request goes to your infrastructure. It has all cookies attached as usual, and the server can generate a personalized response for the user. Whichever request is faster will win this race. In most scenarios, the SpeedKit response will be much faster, especially for pre-cached pages, but the race ensures that the site will never get slower. When the SpeedKit version comes back, the browser uses the HTML to load all necessary resources and renders the page. Once the personalized HTML comes in, it's automatically merged with the current DOM, and the browser kicks off JavaScript execution. This makes sure that all personalized content is displayed, and personalized scripts like data layers are also executed as expected. Almost the whole process works automatically. The only thing that needs to be configured are parts of the anonymous page that should not be shown to the user until after the personalized content is merged. As an example, we have visualized this for the cart icon at the top. This configuration is simply done via CSS, and we'll see a concrete example on the next slide. That said, our engineers prepared the initial configuration for your site, so no changes on your end are necessary. Before we go to the next slide, there are two more things to highlight here. Besides merging the personalized content, we also need to make sure that the cached page is always up to date, as changes to the content happen continuously. To guarantee this, we compare the cached page to the freshly loaded one to find differences in the not personalized content. If we detect the change, we report this to our server, which in turn refreshes the cache entries. This way, we're crowdsourcing the task of keeping the caches up to date and are making sure that for every change, only one user sees a quick shift from the cached content to the up-to-date one. Besides content changes, we also need to update our caches after deployments of the application. To achieve this automatically, we detect deployments by monitoring the linked resource URLs with their versions or hashes. If a resource changes, we infer a deployment and purge the full server-side cache as well as all client caches before building it up asynchronously in the background. To recap, SpeedKit caches anonymous HTML files. Hiding areas in the cached version is easily done via CSS. Personalization is merged automatically once the server response is received. Cache updates are crowdsourced via change detection, and the cache rebuilt automatically after deployments. Before we move on to how our prediction models work, let's take a quick look at the CSS rules to style content on cached pages. The cached page has a class on the HTML element called SpeedKit Dynamic Loading. Once the personalized content is merged, this class changes to SpeedKit Dynamic Loaded. This means you can simply define CSS rules as on the right that style the cached page, and they're automatically disabled as soon as the personalized content is merged. As an example, we have visualized this for the cart icon at the top. This configuration is simply done via CSS. That said, our engineers prepared the initial configuration for your site, so no changes on your end are necessary. Now that we covered all about caching in detail, let's take a look at how our prediction works. To get the most accurate predictions, we combined 3 different models that contribute to the final decision. The first model uses link metadata and user behavior to train a lightweight model on our infrastructure, using real user monitoring data and user behavior on the device to ensure high accuracy. The data we used here includes, among others, scroll speed, cursor or touch proximity, link position, size, and visibility, as well as content. The key advantage of this approach is that we can score links extremely fast and use data only available directly on the user's device. The second model is trained on user journeys and the content of pages. We used embeddings to capture the meaning of URLs instead of relying on pure transition probabilities like approaches that use Markov chains. This model runs in our infrastructure as it is very large and complex. An API sends recommended links to the client that are considered for pre-caching. These 2 main models are complemented with device-specific heat maps that score links depending on the temperature on the screen area. The combination of these models has proven to be very successful, reaching a recall of over 85% with very early pre-caches, giving the browser plenty of time to render in the background. See this last slide to read up on details for each of the discussed models. This concludes this in-depth overview of SpeedKit. Thank you so much for watching.